Here we're going to cover the cross product, and we're going to talk about the cross product in terms of math, in terms of the mathematical definition. We're not going to talk about moments in specific here, but I'm kind of giving you a little bit of a preview. Basically, the moments calculation that we've been doing in 2 dimensions is kind of a simplified version because it's in 2 dimensions. But in reality, it's a cross product of 2 vectors. And when we get to more complicated problems in 3 dimensions, it's difficult to do this 2-dimensional calculation. So what we do is resort to cross product in 3 dimensions. So you're going to need a couple of tricks in your tool bag in order to be able to calculate vectors, vector cross products. Now I know that everybody watching this has actually been exposed to cross products before. You've probably been exposed to it in a physics course. You've probably been exposed to it in a calculus course. But just in case you're joining me now for the first time and you haven't taken those classes with me, I want to do this section and do it justice on the cross product. I'm going to warn you a little bit. It's going to get to be a slog to get through it in the middle. But I think sometimes when I teach these classes, it's worth 5 extra minutes to go through, or maybe 15 extra minutes to go through some details. But when we get to the end of this lesson, I guarantee you that you will be more confident in your understanding of the cross product than when you started, unless you just use these things all the time. Maybe you already have that insight, but I bet most people watching it will be more comfortable at the end. So just get through it with me, I guess is what I'm trying to say. I promise there's a point to it. All right, so the cross product of 2 vectors. We've already talked about the dot product a long time ago, and the complement to that, or the alternative to that, sometimes we end up using the cross product. So we say vector C is equal to the cross product of vector A times vector B. Now you should know, since you've taken classes before, that this is not a straight multiplication. This X, it indicates a cross product. And since vectors have magnitude and direction, then when we operate and cross A into B, then the resulting vector that we get also has a magnitude and a direction. All right, so that's a little different right off the bat than the dot product. Remember, we dot 2 vectors together, we get a number back, a scalar. You just get 4 or -3 back for a dot product. But for a cross product, you're always going to get a vector back. Okay, A cross B will give us the vector C. Now the magnitude of this cross product, or the magnitude of the result here, is something that we can use occasionally here. The magnitude, notice I haven't put any bar on the top of it, so you can say the magnitude of the vector C is equal to the magnitude of A times the magnitude of B, right? And times the sine of the angle between these guys here. This is a direct analog, or at least a direct comparison to what we did in the dot product. Remember, in the dot product, we said the magnitude of the dot product can be, of A dot B, is A times B times, or magnitude of A times magnitude of B times the cosine of the angle between them. Now this should look somewhat similar to you. If you remember, the dot product was defined as magnitude of A times magnitude of B times the cosine of the angle between them. And this is real similar, magnitude of A times magnitude of B times the sine of the angle between them. But when you do this calculation in terms of a cross product, what you're getting back is the magnitude of the vector that's the cross of those 2 guys here. So the magnitude of this vector that's the cross product here is given by this calculation. But since it's a vector, it also has a direction. So the direction of this cross product is given by the right-hand rule, which we've already given you a preview of, because in some of those moment problems I was kind of trying to tell you, hey, if you curl your fingers and your thumb comes out in the direction of the moment. So it shouldn't come as no surprise. The moment is going to end up being the cross product of 2 vectors. It's going to be the cross product of the force and the moment arm, basically. And we have a direction associated with that, which comes about from the right-hand rule. So to draw a picture of that, and to make sure you understand this, it's easy to do that here. So you got to use your imagination a little bit, because I'm drawing on a 2-dimensional board, and really I'm trying to represent something that is 3-dimensional in nature. So this has an angle theta between them. So if you can imagine, I know it's kind of hard, but imagine these 2 vectors being in the same plane, like on a sheet of paper. Then I think when I draw this third one, it'll be a little bit clearer. The cross product of A cross B is going to be coming out of the plane here, and I'll draw it really high, something like this. Vector C is A cross with B. So you got to imagine a sheet of paper lying here. I know I can't draw it on a flat board like this. In the plane of this paper is vector A And also vector b. I know I had to draw it up like that, but that's because I'm drawing it on a board. But basically, vector a and vector b are in the same plane together. If I then cross a into b, I know it's drawn like this, but you got to realize it's in the same plane. Cross a into b, then the vector c, the direction of it is given by the right-hand rule. A cross b, you always cross the first vector into the second. So I'm going a cross b like this. Remember, they're in the same plane. Vector c goes straight up out of there. Okay, so a couple notes, I'm not going to write them down, but I'll make sure you understand them. If theta becomes 90 degrees, sine of 90 is 1, and the cross product is going to be a maximum because you'll have magnitude of A times magnitude of B. This will be 1 if you have 90 degrees, sine of 90. So the magnitude of the cross product is a maximum when you have 90 degrees. This should come as no surprise since I've already hinted to you that the moment that we've been calculating is basically a cross product. If you notice, the whole time we've been looking for when does the line of action cross with the moment arm at 90 degrees, right? Because that's when the moment is the maximum. So 90 degrees is important. That all comes back to this cross product thing here, because what we end up having here, 90 degrees, when you have a 90-degree angle here, the cross product is maximum, okay? If you end up with an angle between these two vectors of 0 or 180, that means that these two vectors are going to line up with one another, and the cross product will be 0. So in order to have a cross product, you need to have some angle between the two vectors. Now remember, this is in the like a plane here. So what I'm saying is, when I have A and B at 90 degrees to one another, I know it's kind of hard to see at 90 degrees, then vector C will be a maximum. The cross product will extend out of the plane by the right-hand rule at a maximum. But if these two vectors are lined up on top of one another at 0 degrees, so A and B are kind of collinear, then the cross product is 0, because sine of 0 degrees is 0. Same for 180. That would mean the vectors flipped over and they're both lined up that direction. The third note I want to say is the direction of the cross product. It always follows the right-hand rule, but it may not realize it yet, but the direction of the cross product is always in a direction perpendicular to the plane that contains your original two vectors A and B. So in this case, we have A and B. If you're doing cross products, you're always going to be crossing them with the right-hand rule, and so the cross product is always going to come out of the page. Another way to look at that is if I have vectors on the board here and I cross them, the moment or the cross product always coming out of the plane that contains those two original vectors. Always comes out of that plane, perpendicular to it. This one warrants writing down. I'll tell you this right now. If you have A cross B, that is not the same as vector B crossed with A. It's not the same. It is not the same because the cross product has direction. If I cross A into B, remember it's in the plane here, A into B, I'm going to get a vector pointed up like this. But if I cross B into A, that means I need to cut my fingers through vector B first. If they were the same vectors here, then I would be cutting oppositely, and the cross product would go down. So remember, a vector is magnitude and direction. So if I cross A cross B, I'm going to end up with a cross product going one way. But if I flip my fingers to curl and go the opposite way, B cross A, the cross product is going the exact opposite way. So those two things are not the same. Even though the magnitudes might be the same, the directions aren't the same. And so that's just that's something that you always have to consider. Now, that's different than the dot product. The dot product didn't matter which direction you dotted. And that's why I'm pointing it out here. When you have a cross product, you can't flip them because it's not straight up multiplication like you learned in third grade. It's a little more complicated than that. All right, so now we want to learn about something that I think gives students problems sometimes, but it's very easy to understand. I want to teach you how to cross, so I'll say crossing unit vectors. Because crossing unit vectors is the key to understanding how the cross product really works. And so what I want to do is let me draw a little three-dimensional situation here. So let me go ahead and draw, let me think about how to do this. I'll do it right here. Here we have this guy here, and we have the X direction, we have the Y direction, Z direction, just like this. Now, because this is X, Y, and Z, you should know, and I'll use black here, you should know that this guy here, there's actually a unit vector, which is just a vector pointing along the X direction with a length of 1. We call that unit vector I hat, right? It's pointing along the X direction. And then we have a same unit vector, or same length of the unit vector pointing in the Y direction. We call this J hat. And then we have the same length of a unit vector pointing in the z direction. Maybe make that a little taller, like this. And we call that k hat. So ijk, we've been using this all the time, okay? But what I want to show you is what's going to happen if you try to cross these vectors into each other in different ways. I mean, don't forget, these unit vectors, they're not magical. They're just vectors that point 90 degrees from one another, and they have a length of 1. Other than that, they're just regular vectors. You can cross unit vectors just like you can cross any vector, because they are vectors. They just have a length of 1. So let me draw a little table here and see if I can make this a little bit clearer for you. Okay, so if I'm going to have, I can have I, and I can have j, and I can have k, and I can, let me go ahead and maybe move this down just a little bit. Let's do it over here. I can have I can have j, and I can have k, like this, right? And I can cross it with I, j, let me give myself a little more space, j or k. Okay, so basically there's a bunch of different combinations here I can cross these guys with. So let me go ahead and do something like this. All I'm doing is drawing a table here. Basically, I can take vector I can cross it with itself. I can take vector I can cross it with vector j. I can take vector I and I can cross it with vector k. What's going to happen in each of these cases? Well, you can just use the right-hand rule. I don't want you to calculate anything with math. I just want you to use your fingers. That's all you want to do. So what's going to happen if I take I and I cross it with itself into I? Well, we already said before that if I have two vectors that are lined up on top of one another, the angle between them, 0, sine of 0 is 0. So anytime I have a vector crossed with itself, I just get 0 because there's no way to cross it. I mean, it's just two vectors sitting on top of one another. You can't really cross it because the angle between them is 0. There's no angle that's there between them that you can actually sweep one into the other, and so you're not going to get a cross product. Okay? And the same thing happens when you try to cross j into j. And the same thing happens when you try to cross k into k, because those vectors are just sitting on top of one another, and you don't get a cross product when that happens, because the sine of 0 is 0. But I can cross I into j without any problems. And to do that, you need to take your fingers and first cut them from I and sweep them into j. My thumb is now pointing up, which is in the k direction. So whenever I cross I into j, I get a new vector called k. Notice that k is perpendicular to the plane that contains I and j. That's what we always said is true with cross products. The cross product answer that you get is always going to be perpendicular to the two vectors that you start with, to the plane that contains them. All right? Now I can also take I and I can cross it into k. Right? I know it sounds a little weird, but if I take my fingers, if I cut through I and then cut through k, my fingers are going to be going, if you kind of visualize it this way, they're going to be going opposite of what the way this way is pointing. So they'll be pointing in the negative j direction. Don't forget, this is the positive j direction. The negative j direction just goes this way. The negative k direction goes down. The negative x direction goes that way. So if I sweep I into k, then you can visualize that I'm going to be pointing in this opposite direction, which is negative j. Now we'll speed things up a little bit. If I'm going to go j crossed into I, j crossed into I, cut into j first, then into I, my fingers are pointing down, which is negative k direction. And then if I'm crossing j into k, I cut into j first, then into k, and you can see that I'm pointing in the I direction, which is like that. And then k crossed into I, cut through k, then into I, I'm pointing in the j direction. And then if I cross k into j is going to be, if you kind of use your imagination a little bit, k into j, that's going to be the negative I direction. Now it's a little hard to visualize it completely because this is a three-dimensional drawing on a two-dimensional board. But whenever you got to do a little mental gymnastics to kind of do that, but you really should get used to that because whenever you're doing these problems, they're all going to be drawn on a piece of paper. So you have to kind of get the mental gymnastics of crossing them in, with your fingers and which direction they're pointing. So notice there's some symmetry here. You have zeros along the diagonal, you have k's here, but this one's negative, of course. You have j's here, but one of them's negative, and you have i's here, and this one's negative here. So I have a negative here, a negative here, and a negative here. I'm just checking everything here to make sure I haven't lied to you. So this is a chart. Now, you don't need to really keep this chart around. I'm just doing it to kind of give you practice. The reason I put it here is to mostly show you how to do it. You could write this down and use it as a reference, but really it's just easier to draw the unit coordinate system and just cross with your fingers. If you're trying to go J into K, then just do that. If you're trying to go K into J, go the opposite way, and so on. Okay? What I want to do next is I want to show you how to cross two vectors in the kind of the long way. Remember, they're just vectors. They just have a magnitude and an associated direction. Let me think. Maybe I can do this on the other board. Let me switch this through like this. Okay. What if I had two vectors? I wanted to cross A and cross it with B. Now these aren't unit vectors anymore. Let's say vector A is 1i plus 2j plus 3k. And that's a vector. And I'm going to cross it in with another vector that I'm going to write right here, which is 4i plus 5j plus 6k, like this. So this is vector A, that's this guy, so I'll just write it down here. This is vector A, and this is vector B. Notice I have 1, 2, 3, 4, 5, 6, just to make it a little bit easier, but these numbers can be anything. This is an arbitrary vector in three-dimensional space. This is another arbitrary vector in three-dimensional space. Now I'm going to kind of give you a little preview here before we do this. There is a hard way to do this. I'm going to show you that first because I think it's important for you to know where it comes from and that the cross product is not magical. I'll show you the rules to calculate it. But then when we get through that, I can kind of show you a much easier way that's much easier to remember. It's not that it's really the same math, it's just easy to remember. And the cross product, the reason I'm spending time on it is because you use it in mechanics, but you also use it in electricity and magnetism, and you use it in thermodynamics, and you use it in physics, and you use it everywhere in pure math. It's one of those things like multiplication that you just use everywhere in engineering. So I really want you to get a good foundation in that. Now, if we're going to cross these two things together, and we are, notice you have three terms here and you have three terms here. So if this were not a cross product, if it was just multiplication, how would you do it? You would take the first thing here and you would multiply by this and then with this and then with this and add them together. And then you would move your finger here and then you would multiply this times this, then times this, then times this, and you'd add all those together. Then you would move your finger here and you would multiply this times this and then this and then this, and you would add them all together. When you have large trinomials like that with three terms and you're multiplying them, I mean, I know you can dump it into a computer and get the answer, but all that's happening is you're taking each term and multiplying by the other terms. You're taking the next term, multiplying by these terms, and then you're taking this term, multiplying by these terms, and then you add all of everything together and you simplify. And that's how you multiply things in algebra, really. Okay? Now, the similar thing is going to happen in this cross product, okay? Because what we're going to have is it'll be this crossed with this. Now, the numbers out in front just simply get multiplied together. So 1 times 4 will be 4, but the vectors here, you can't just multiply them. They have to be crossed, okay, because they're a vector. So when they're crossed like this, it's I crossed with I crossed with I. Now, I'm not going to do this cross product now. What I want to do is write all the terms out, and then I want to simplify everything. You know from this discussion that I cross I is 0. There's nothing there. Because you can't, when you cross a vector with itself, there's no angle between them, so it drops to 0. But for the purpose of this, I want you to put your finger here and cross it with this. 1 times 4 is 4. I cross I, we're going to write down here. Then I'm going to add to it. Keep my finger here. I'm going to do this guy. 1 times 5 is 5, and then I cross J. I cross J. Okay, I'm not going to do that yet. I'm going to write it down. I'm going to say plus. I'm going to keep my finger here. It'll be this one crossed with this one. 1 times 6 is 6. I cross K. Okay, you should sort of start to see a pattern here. Now we're going to move to the next line. And I'll move my finger from here to here. And again, I'll start over like this. So this crossed with this. 2 times 4 is 8. And then I have J crossed I. J crossed I. And then I'm going to have this. 2 times 5 is 10. J cross J. You should already know that J cross J is 0, but we're just going to write it down for now. And then here, 2 times 6 is 12. And then I have J cross k from this to this. And then I go down to the next line. And then I move my finger. See, I was doing this one, then this one, now I do this one. 3 times 4 is 12. And then I have k crossed with I, right? And then I have this guy here. 3 times 5 is 15. K cross j. Like this. And then I have 3 times 6 is 18. K cross k. Which you already should know is 0. And I've said it enough times that basically you know now that I cross I is just going to go to 0, j cross j is going to go to 0, and k cross k also goes to 0, because anytime you cross a vector with itself, you get 0, because there's no angle between them. All right, so now what we need to do is simplify this guy. That's really all that remains to be done. So let me just double check that I haven't made any mistakes here. We have 5, I cross j, 6, I cross k, 8, j cross I, 12, j cross k, 12, k cross I, 15, k cross j. Okay, that's right. So then, the next line. 4 times 0 is 0. We don't have to write anything there. 5, what is I cross j? Now, I can just look at my table. I cross j is k. But if I don't have this table, I just draw x, y, z. I cross j, just cross I into j. That gives you a k component. So what you're going to have here is k. The 5 comes from the multiplication. The vector direction comes from the cross product of I and j. Then I have 6 coming from here, and I cross k. What is I cross k? Well, I, when I cross with k, is negative j. You can check I cross k is negative j. That's exactly what we have. So I'll just put the negative j here. I could put the negative here. I'm going to do that in a second step. I just want to keep things clear. Then I have 8. J cross I. And j cross I, you can cut into j, then into I, is going to give you a negative k. That was this one. Now we have the 12. J cross k. J cross k, you can cut it into there, it's going to give you a positive I. And then over here you have a 12. K cross I. K cross I is going to give you this guy, which is going to be a positive j. And then we have 15. K cross j. K cross j gives me negative I. K cross j gives me negative I. So you can do it with the right-hand rule like that. All right, so now we can simplify things here, because now you have to simplify these things. It's just like adding algebra, right? When you add things up in algebra, 2x plus 3x, it's 5x, because you're attaching it to the x's, right? 2j plus 2j, 4j. So because these are unit vectors, it doesn't really change that. You're still trying to group terms. So for the I components, you have a 12i here and a negative 15i here because of this negative sign. So what you end up with is negative 3i right there. And then for the j components, we have these guys. We have 12 and a negative 6. So that'll give us a positive 6j. And for the k components, we have the 5 and the negative 8. So again, that's negative 3 in the k direction. This is the cross product of A, crossed with B. So notice there's an I component, a j component, and a k component. It's pointing obliquely in three-dimensional space someplace. The original two vectors were pointing obliquely in three-dimensional space someplace. You can have negative components here, positive components, but you should always get a three-dimensional representation for a cross product in general. Now, this works bulletproof every single time, but it's just a little cumbersome because you have to write vector A and write vector B down, and then you have to essentially cross everything with every other thing, and then you have to simplify the cross products, and then you have to add everything up. It's bulletproof, but it's just a little bit ugly. It's just not very nice to do. Okay, so what you would typically find in your book is, in general, you'll find a formula for the cross product as follows, and it'll be written like this: A crossed with B. A crossed with B. And it's going to look ugly. I'm going to warn you right now. This is how you write it in general. A y b z minus a z b y in the I direction. That's the I component of this answer. And then you have minus axbz minus AZ BX in the J direction, and then you have plus some K component here, which is AX BY, whoops, AX BY minus AY BX, K direction. So this is what you'll typically find in a book. When you learn about the cross product, they'll teach you what it is, and then they'll put this thing in front of you, and normally you'll kind of like throw up in your mouth a little bit because it just looks ugly. Let me make sure I wrote it down right. AY BZ minus AZ BY in the I direction minus AX BZ minus AZ BX in the J direction plus AX BY minus AY BX in the K direction. So what does all this stuff mean? See, this is vector A and this is vector B. Now this is the X component, A sub X. This is the Y component, A sub Y. This is the Z component, A sub Z, okay? Then you have B sub X, B sub Y, B sub Z. So for each vector, A and B, you have an X and a Y and a Z component. So all you do is you just plug it in here. The Y component of A times the Z component of B, get that multiplication. Then you subtract it from this product, the Z component of A minus the B component of Y. So this is going to give you a number, and then you're going to, that's going to be the X component of this guy. And then you do a similar calculation for that guy there. So what I want to do just really quickly, and I'll move over here, is to show you that this is actually true. So for our particular set of vectors here, AX is 1, AY is 2, and AZ is 3. And over here we have 4, 5, 6. So BX is 4, BY is 5, BZ is 6. So we have XYZ for A and XYZ for B. So if I wanted to use this canned formula for the cross product, the way I would do it is I would say A cross B is equal to the following. So AY, which is 2, okay, BZ, so BZ would be 6, so 2 times 6 is 12. So what I would have is 12 minus, and then I have AZ, which is 3, minus BZ, which is Y. So these guys here, this would be 15. That's in the I direction, because it's the I direction here. Then I have a minus sign here I have to keep track of. Okay, AX minus BZ, or AX times BZ. So 1 times 6 gives me 6. And then AZ minus BX, or AZ times BX, sorry. 3 times 4 is 12. And that's in the J direction. And then plus, here we have AX BY, 1 times 5 is 5. And then AY BX, 2 times 4 is 8. And the K direction. So what this is going to be, 12 minus 15 is negative 3I, okay? Actually, let me just make it a little bit clearer. I'll switch colors. Negative 3I. 6 minus 12 is negative 6, but then I have a negative out here, so it's positive 6. J. And then 5 minus 8 is negative 3. K. So negative 3I plus 6J minus 3K. Negative 3I plus 6J minus 3K. So all of that showing that if I just bust out and do everything manually, I get the same exact thing that you typically get in your textbook. All right, believe me, I know it is tough to follow all of this and to care, okay? But cross products are going to be a part of your everyday life. You're going to be doing them all the time in mechanics and other classes. So let's take just a few minutes to review where we've been. All right, what we said is there's this thing called a cross product. The magnitude of it is AB sine theta. The direction is purely given by the right-hand rule. Okay? Then we said that the right-hand rule works by curling your fingers and looking where your thumb points. So for any unit vector, we can cross any combination and we can figure out where it's going to point with the cross product. Then I tried to lock it down with an example. Arbitrary vector A, arbitrary vector B, cross everything with everything else and simplify and you get an answer. And then this is what you're given in your book. This is where it comes from. All of this stuff, if you mathematically simplify it down, you can derive this. This thing really is coming from everything we've done above. But I want to simplify things even further for you because even though this is useful, This relation here, this equation, is very hard to remember. You're not going to remember it, at least unless you really try hard. And even if you do remember it, you can easily make a mistake. Did you notice how it was like ax times by and so on, and then crossing it the other way? It's very difficult to do. So here we're going to learn about some of the most useful things I've ever learned in my life. And this one's called the cross product as a determinant. All right, as a determinant. And it's very easy to write down, and it's very easy to implement and allow you to calculate cross products till you're blue in the face very, very simply. Here's how you do it. A cross B can be written as the determinant of a matrix. So what I'll write it is I'll say like this, the determinant of a matrix. And the matrix is formed by putting I, J, and K in the top. And then you have the X component, the Y component, and the Z component of A, and the X component of B, the Y component of B, and the Z component of B. There. Now, at some point, I know this doesn't look any simpler yet, believe me, but it will. At some point in your past, you probably studied matrices, and you should have learned how to calculate the determinant of a matrix, specifically how to calculate the determinant of a 2 by 2 matrix. And if you remember that, or if you go back and review it from what I've taught you, the determinant of a 2 by 2 matrix is a crisscross pattern. It's you multiply the diagonals and you go the other way and multiply the diagonals. So if you don't even know what a determinant of a matrix is and have no idea and you haven't studied it for 15 years, probably should take a second and go review what a determinant of a 2 by 2 matrix is and what a determinant of a 3 by 3 matrix is here. I'm going to give you a practice problem or two here to nail it down. But you need to realize that the cross product of two vectors is written as the determinant of a 3 by 3 matrix, where we write it with the components of the vectors like this. So for instance, if I have vector A, which is 2i plus j plus k, and I have vector B, which is I plus 2j plus 3k, I want to cross these guys together. Of course, I can use the formula on the previous board, or I can bust it out manually, but instead I'm going to choose to write it down as a cross product. So I'm going to say that vector A cross with vector B is the determinant of the following matrix. The first line of the matrix is always just the unit vectors. That's what makes this so easy, right? Then the next line is your A vector, and it's just the numbers, the X and the Y and the Z component. That's all this represents. So you put 2, this is a 1, and this is a 1. You put numbers there. It's very simple. And then for vector B, this is going to be 1 from there, 2 from there, and 3 from there. So basically what you do is you write down the unit vectors, and then if you're going A cross B, the first vector here, the vector A, the components get written in the second line, and vector B, the components get written in the third line. Now all you need to do is learn how to calculate the determinant of this matrix, and then you got the answer. Okay? So let me show you how to do that. It's really simple. What you do is, first of all, you kind of draw a line through this column and a line through this column, okay? So they intersect at the I location. So the first component you're going to calculate is going to be the I component of the answer. So you cross through this, you pretend it's not even here. And you cross through this, you pretend it's not even here. If I had two pieces of paper, I would cover this up and I would cover this up. So all that's left that I can actually see are these 4 numbers. Now I need to take the determinant of these 4 numbers, and you should remember from matrices a long time ago, that you multiply these diagonal elements and then you subtract the multiplication of these. So 1 times 3 is 3, minus, that's from this direction, minus 1 times 2 is 2. Okay, you've actually calculated the I component of the answer already. Okay, you didn't have to memorize anything other than you need to know how to calculate this determinant, but you don't have to memorize AZ times BY minus 2, all that stuff. Basically, you just cover this, that's the I component is this multiplied minus this multiplied. Okay, then the next thing you have to remember is very important. You must put a minus sign for your second term, and then you're going to cross through the top, and you're going to cross through this. Now where they intersect is the J location, so you're finding the J component. You must remember to put the negative sign out in front. So if I've covered this up and I've covered this up, the only numbers left are these numbers and these numbers. You need to pretend that those numbers are a nice 2 by 2 matrix here. So you're going to cover these up. You're going to take the determinant as if these were here. So 2 times 3 is 6, minus 1 times 1 is 1. You're basically pretending this isn't there, and you're treating this as a 2 by 2 matrix, 6 minus 1, boom, you are done with the answer to the second component here. And then you can go back to plus. You're going to cover up this column and this guy, which intersects at the K location, so you're finding the K component. Cover this up, cover this up. The only thing revealed is this. 2 times 2 is 4, minus 1 times 1 is 1. All right, so then what you have is A crossed with B is 3 minus 2 is 1, so 1i, you can just write it as I. 6 minus 1 is 5, but there's a negative there, so it's negative 5j. 4 minus 1 is 3, so you get plus 3k. This is the cross product of these two vectors. All right, now let me ask you a question. Even though I had to teach you how to do this, was this easier or was this easier? Or was all of this easier where you had to plug everything in manually and all that stuff? I mean, ultimately, this is doing the exact same calculation. The multiplications here and the subtractions, what you're doing here is exactly what you're doing when you cross out this and this and you do a crisscross multiplication to get that determinant. It's basically, you learn this kind of stuff in linear algebra, but basically the determinant of a matrix like that, that's how you calculate it. You crisscross things and you find the determinant of the submatrices inside, which are 2 by 2 matrices. The only thing you need to remember is that when you're finding the middle term, you have to stick a negative out in front of the j. Now I'm going to do one more real quick and then we're going to call it a day. So I'm going to draw a little line here. If I have A is negative 2i minus 2j plus 3k, and B is I minus j minus 4k. Okay, you could of course put everything into that enormous formula on the other side, maybe not have any way to remember it, but I'm going to encourage you to write it as A crossed with B is the determinant of the following matrix. The first line is always I, j, and k, always. It never changes. Then you're crossing A into B, so you have negative 2 right under here, negative 2 here, and 3 here. And then for B, you have 1, then you have negative 1, then you have negative 4. And now you just have to go through the mechanics of writing down the determinant here. So what you're going to have is, first I go down, I cross out the first column and the first row here. So I'm working on the I component because that's where they intersect, the intersection of these two lines here that I'm crossing out. The only numbers that are revealed or left over are these. So negative 2 times negative 4 gives me positive 8, minus this gives me negative 3. Now, don't get screwed up here. You have to have the minus when you're doing the crisscross multiplication, but the actual thing you multiply also gives you negative. Don't do too many things at once. Write down the minus negative so that you don't mess anything up. Then, cross out this guy, so I'm working on the j component, but I just need to remember to put a negative j here. So I'll cross this out like this. The only numbers left are these. So negative 2 times negative 4 gives me positive 8, minus, then I have 3 times positive 1 gives me a positive 3. Then I have a plus. I'm going to be working finally on the k component because I'll be crossing this out with this. This is what's left over. Negative 2 times negative 1 gives me positive 2 minus, and then I have this minus this. Negative 2 times this gives me negative 2. Again, I need to keep the double negative here so I don't screw myself up. So then at the end of the day, 8 minus a negative 3 is 8 plus 3, which is going to be 11 in the I direction. And then here I have 8 minus 3 is 5, but this is a negative out here, so negative 5 in the j direction. And then here 2 minus a negative 2 is 2 plus 2 is 4, which is plus 4 in the k direction. This is the cross product here. All right, so I've done 2 examples to show you how to cross these things with matrix methods. Basically, you focus on the first column, you cross this out, that's the I component, and then you do a crisscross multiplication with a subtraction in between, basically find the determinant of this little submatrix here. Then you move on to the middle one, make sure and put your negative sign, crisscross these elements minus these, and then you work on the last one, crisscross multiplication of these, and that's what you do. Now, it's really honestly up to you. You're going to be doing a lot of cross products in this class and in lots of future classes. So if you want to, you can just write it out every single time. You can just put everything out, cross everything, figure out the directions of everything, simplify everything. Or if you prefer to memorize this, really this calculation is doing exactly what we're doing with determinants on the other side. You just have to label everything, put everything into the right spot, do the calculations. This stuff here that we're doing in this, using this equation, is exactly what you're doing here. It's just, this is a visual way of representing the crisscross. Notice you're multiplying and you're subtracting. Here you've multiplied things together, like these guys, and you're subtracting it. So really it's exactly the same thing. There's no difference, but this is just a visual way to represent what to do. I'm going on and on about it because to find the cross product of these vectors in this way with a determinant has honestly been one of the most useful things I've ever learned. Because you will be doing a test somewhere, or you will be doing some other class way down the road, and you'll have to cross two vectors, and you won't remember. You won't remember that giant equation, even if you remember it now. But then you'll remember. You'll say, wait a minute, I can write that as a determinant. I'll put ijk on the top, a in the middle, b on the bottom row, and then you just have to remember to go through and crisscross the submatrices, and boom, you're done. So I've talked enough. It's a very long lesson. Thanks for sticking with me. I could have just showed you this at the end. I was very tempted, but I wanted to show you that doing it the long way and kind of the evolution of the ways in which you can calculate the cross product, there's nothing magical about any of that stuff. I just wanted to show that to you and finally culminate in what I really want you to do, which is this way. I'm going to be doing it this way as we go through the rest of the course when I need to calculate cross products. So I encourage you to do the same. Follow me on to the next lesson. We'll be talking about how to use this cross product to find the moment of vectors in 3 dimensions. Learn anything at mathandscience.com.